Welcome, everyone, to this explainer. Okay, let's just dive right into this today because we're starting with a reality check that is frankly as humbling as it is mind-bending. I mean, think about it. For centuries, literally since the dawn of humanity, we have looked up at the night sky and tried to make sense of our place in the cosmos, right? We've mapped out constellations, we've painstakingly tracked planetary motions, and in modern times, we've built these absolutely colossal billion-dollar telescopes to see further than ever before. But here is the haunting truth of it all. Everything we have ever seen, touched, or understood, every single star, every distant galaxy, every planet, the device you're using right now, and you and me, all of it makes up only 5% of the universe. Just 5%.
It's honestly hard to even wrap your head around.
It really is, because that means the other 95%, it is completely invisible, it's totally mysterious, and yet it fundamentally dictates the fate of our entire cosmos. So today, we are going on a journey. We're starting from the comforting, familiar light of what we actually know, and we are heading straight into the terrifying, exhilarating dark of the unknown.
I'm incredibly excited to guide you through this mystery tour today. So here is our agenda. First, the 5% we know. Second, dark matter's invisible grip. Third, the dark energy enigma. Fourth, relativity and black holes. Fifth, the cosmic speed limit. And finally, number 6, embracing the great unknown. Let's get right into it.
Section 1. The 5% we know. Our cosmic address and the Big Bang.
All right, so when we talk about this 5% we know, what we are really talking about is baryonic matter. That's the scientific term. This is just ordinary matter. We're talking protons, neutrons, electrons. This is the stuff governed by the standard model of particle physics. It explains everything from the nuclear fusion that's currently powering our sun to the complex chemistry making up our own bodies.
Wait, I really need to pause here and just absorb this for a second. Are you saying that every single star in the Milky Way, every single distant galaxy we've ever managed to capture with the Hubble or the James Webb Space Telescopes, every living organism on Earth, if you combine all of that, it only accounts for 5% of the universe's mass and energy?
That's exactly what I'm saying.
That is absolutely staggering. It's kind of like, thinking you understand the entire ocean just because you've looked at the sea foam riding on top of the waves.
I love that analogy, and it is incredibly accurate. That tiny 5% sliver of baryonic matter, our seafoam, is completely overshadowed by these massive invisible entities. If you break down the cosmic inventory, roughly 27% of the universe is dark matter, and a massive 68% is dark energy. And the kicker here is that they don't emit light, they don't absorb light, they don't even reflect light. They are entirely invisible to all of our traditional instruments. Yet, as we're going to see, they are the unseen architects and the ultimate drivers of the cosmos.
Okay, but playing devil's advocate here. If we only know 5% of what's out there, how can we possibly be so confident in our own cosmic origin story? Like, why do we trust the Big Bang Theory so much if we're mostly in the dark?
You know, that is exactly the right question to ask, and it's a super common one. We trust it because we have 3 incredibly robust pillars of observational evidence. We didn't just guess this stuff. First up, back in the 1920s, Edwin Hubble noticed that galaxies were moving away from us. It's called Hubble's law. Picture a balloon that you've drawn little dots on. As you inflate that balloon, the rubber stretches, and every dot moves further apart from every other dot. That is our expanding universe.
Right, the universe itself is stretching.
Exactly. Then, the second pillar. In 1964, Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background, or CMB. They were actually working on a radio antenna and thought pigeon droppings were causing this weird static. But no, it was a faint 2.7 Kelvin glow coming from literally all directions. It is the literal afterglow of the Big Bang, frozen in time from when the universe cooled down enough for light to travel, about 380,000 years after the beginning.
Imagine mistaking the birth of the universe for pigeon droppings.
Right? A real cosmic oops. And the third pillar is Big Bang nucleosynthesis. It perfectly predicts the exact abundance of the light elements we see out there today. If the Big Bang happened, the math says the universe should be about 75% hydrogen and 25% helium. And when we look out, that is exactly what we measure. So, the 13.8 billion-year-old Big Bang, it's not a shot in the dark. It is heavily documented history.
Section 2. Dark matter's invisible grip. The gravitational ghost. All right, so stepping into the 95% unknown. Back in the 1970s, an astronomer named Vera Rubin was mapping galaxy rotation curves. Basically, she noticed that galaxies were spinning way too fast, Based on the visible stuff inside them, they should literally be flying apart, so she realized there had to be some invisible missing mass holding them all together with its gravity. But if dark matter is completely invisible, how do we actually prove it's really there? We see it by watching how it bends space. It's a phenomenon called gravitational lensing. When light from a super distant galaxy travels toward us and it passes by a massive cluster of dark matter, the extreme gravity of that dark matter physically warps the space-time around it. It bends the traveling light just like a giant cosmic magnifying glass. By studying those optical distortions, astronomers can map out exactly where the invisible mass is located. That's brilliant. It is. And the ultimate undeniable proof of this was something called the bullet cluster. This was an ancient collision of two massive galaxy clusters. When they crashed, the visible normal matter, the hot gas, slammed together in the middle and slowed down. But the gravitational lensing showed us that the invisible dark matter didn't interact at all. It just kept right on going, separating entirely from the normal matter. That proved once and for all that dark matter is real, and it acts as a distinct, structure-forming glue for the universe. To really appreciate how fast our understanding has shifted, just take a look at this timeline. In merely a century, we went from Einstein's early 1917 theories to mapping the CMB in the 60s, to Vera Rubin's dark matter in the 70s, and then to an absolutely shocking discovery in 1998 that we'll cover in just a second. But sticking to dark matter for a moment, what actually is it? The leading theoretical candidates are things called WIMPs, which stands for weakly interacting massive particles, and axons.
So how do we build an experiment to find a particle we don't even fully understand?
It takes extreme engineering. Right now, humanity is running massive experiments deep, deep underground to shield them from everyday cosmic rays. We're talking about projects like Lux, Xenon, and Pandax. They are basically sitting in the dark, waiting for the faintest, tiny collision of a dark matter particle bumping into a normal atom in a vat of liquid xenon. It is literally humanity's greatest ongoing ghost hunt.
Section 3. The Dark Energy Enigma. The Cosmic Anti-Gravity.
Okay, wait. Earlier we said gravity pulls things together, right? That's what dark matter is doing. But if that's true, how on earth can the universe's expansion be accelerating? Wouldn't all that gravity be hitting the brakes?
Exactly. That is what every single physicist on the planet assumed. We thought the universe's expansion was slowing down, but in 1998, observations of exploding white dwarfs, specifically Type 1a supernova by scientists Perlmutter, Rees, and Schmidt, proved the exact opposite. Their discovery was so monumental it won them the 2011 Nobel Prize. They found that a mysterious force, which we now call dark energy, is actively pushing spacetime apart.
So it's basically a cosmic tug-of-war?
Exactly. On one side, you have dark matter, the cosmic glue, trying to pull galaxies together. On the other side, you have dark energy, the cosmic accelerant, pushing everything away with negative pressure. And remember that pie chart? Dark energy makes up 68% of the universe. It is winning the tug-of-war. Which means, depending on how this plays out, our universe might end in a big freeze, where everything just drifts infinitely far apart, or maybe even a violent big rip, where the fabric of spacetime itself just tears.
Now, the real irony of this entire dark energy mystery actually traces all the way back to 1917. Albert Einstein was trying to make his equations fit a static universe, one that wasn't expanding or contracting. So he added this mathematical trick to his equations called the cosmological constant just to keep it stable. Later, when Edwin Hubble proved the universe was expanding, Einstein took it out and supposedly called it his biggest blunder.
Ouch. Even Einstein makes mistakes.
But here's the wild part. That blunder might actually be the exact answer to dark energy. Today, the cosmological constant perfectly describes something called vacuum energy. It's this intrinsic energy of empty space itself, where tiny quantum particles are constantly popping in and out of existence. But here is the problem, and why dark energy is called the most embarrassing problem in modern physics. When we try to calculate how much vacuum energy there should be using quantum mechanics, the answer we get is wildly, ridiculously too big compared to what we actually observe. The math is completely broken, yet Einstein's blunder remains our absolute best mathematical fit for what's happening.
Section 4. Relativity and Black Holes, Prisons of Space-Time.
So, transitioning a bit, let's look at the extreme physical consequences of gravity. Einstein's theory of general relativity taught us that gravity isn't just some invisible tether pulling planets. It's the actual physical warping of the four-dimensional fabric of space-time. When a massive star runs out of fuel and dies, it collapses and it warps that fabric so severely it creates a literal prison, a black hole.
And just looking at this number, the supermassive black hole at the center of our Milky Way galaxy, Sagittarius A star, is 4 million times the mass of our Sun. That scale is just terrifying.
It really is. And for decades, black holes were just these abstract mathematical curiosities. We couldn't see them. But that changed recently. In 2015, the LIGO Observatory physically felt the ripples in spacetime, literal gravitational waves washing over Earth from two colliding stellar mass black holes far away. And then it got even better. The Event Horizon Telescope Network captured the first actual image of a supermassive black hole in the galaxy M87 in 2019, and then they got a picture of our very own Sagittarius A star in 2022. We are now literally taking pictures of the invisible.
But as cool as they look, you absolutely do not want to get too close to one. Surrounding every black hole is the event horizon. This is the boundary, the mathematical point of no return, where the escape velocity to get away is faster than the speed of light. Since nothing is faster than light, nothing can escape. If you were unlucky enough to fall in, the gravity pulling at your feet would be so incredibly much stronger than the gravity pulling at your head that you'd be stretched out into a long, thin noodle.
And physicists actually use the word spaghettification for this, right?
They do. It's an incredibly morbid but accurate term. You'd be spaghettified and pulled inexorably down into the singularity at the center, where all our laws of physics just break down. Now, interestingly, Stephen Hawking theorized that because of weird quantum effects happening right at that event horizon edge, black holes aren't completely black. They actually emit a very, very faint thermal glow, which we now call Hawking radiation. This means that theoretically, over trillions and trillions of years, these cosmic prisons might slowly evaporate into nothingness.
Section 5. The cosmic speed limit. Space, time, and the universe's limits.
Now, we mentioned that light can't escape a black hole, but why is light the ultimate limit? It all comes down to special relativity and the famous equation E equals mc squared. That equation tells us that mass and energy are interchangeable. Because of this, as an object with mass speeds up, it requires more and more energy to keep accelerating. To accelerate any massive object all the way to the speed of light would require an infinite amount of energy. Therefore, it's impossible. It is the absolute, unbreakable cosmic speed limit of reality. Faster-than-light travel just isn't happening without violating causality itself.
And that speed is exactly 299,792,458 meters per second. Fast, but finite. And honestly, it's kind of wild to think about. Because it takes time for light to travel, looking out into space is literally looking back in time. Like when we look at the Andromeda Galaxy, our closest large galactic neighbor, the light hitting our telescope right now left there 2.5 million years ago. We are seeing it as it was before modern humans even walked the Earth.
Exactly. Out in the cosmos, a light year is a measure of distance, but it is just as importantly a measure of time.
And this leads us to one of the most beautiful, but honestly deeply melancholic truths in astronomy. Because the universe is just so unbelievably vast, and light takes so long to travel across it, many of the brightest, most beautiful stars we admire in the night sky have already exhausted their nuclear fuel and died. They might have exploded as supernovas thousands or millions of years ago, but their light is still making its long journey to our eyes. We are looking at ghostly echoes of things that no longer exist.
Wow. That means communicating with the distant universe is fundamentally impossible. Does this mean we are just completely isolated in the universe?
In a way, yes. And it gets worse. Because remember dark energy? It's accelerating the expansion of the universe. This means distant galaxies are receding from us faster than the speed of light. Because of this, there's a cosmic event horizon. Much of the universe is fundamentally unreachable to us forever, and eventually over billions of years, those galaxies will fade from our view entirely, as their light can no longer reach us. As cosmologists sometimes say, we are prisoners of geometry.
Section 6. Embracing the Great Unknown. UFOs/UAPs and scientific skepticism. Let's bring this explainer back down to Earth for a minute. Literally, recently there's been a massive cultural shift because of the 2021 Pentagon reports on UAPs, or unidentified aerial phenomena. It feels like overnight this topic shifted from fringe, tinfoil hat conspiracy to actual institutional scientific acknowledgement.
Absolutely. It's been a wild pivot. And the multi-million-dollar question in the scientific community right now is this. Are these UAPs just part of the 5% we already understand, or are they a window into that 95% unknown we've been talking about?
Now, when we break it down objectively, the vast majority of UAP sightings fall firmly into the known 5%. We're talking about misidentifications of commercial aircraft, weird atmospheric and weather anomalies, conventional drones, or just sensor artifacts on sophisticated radar and cameras. But there's a very tantalizing, very small sliver of cases in these official reports that remain truly unidentified.
cases where objects seem to display flight characteristics that currently challenge our understanding of aerodynamics and physics. However, and I cannot stress this enough, it is vital to remember that unidentified absolutely does not mean alien. As humans, our brains have this built-in cognitive bias that just loves to jump to the most extraordinary sci-fi explanations right away. But if we want real answers, the only way forward is strictly applying the scientific method. That means rigorous, standardized data collection using multiple advanced sensors. It means painstakingly eliminating all conventional explanations first. It requires subjecting the data to open, transparent peer review by the global scientific community. And finally, it requires a willingness to revise our current theories based purely on what the evidence shows, not what we want it to show.
So instead of jumping to conclusions without evidence, we need to ask if UAPs are maybe a symptom of our incomplete understanding of physics.
Hit the nail on the head. Whether these anomalies turn out to be highly advanced, classified terrestrial technology from a foreign nation, an undiscovered atmospheric plasma, or something else entirely, we must keep our biases in check and let the data lead the way.
So we have traveled today from the familiar realm of protons, normal matter, and stars, straight out into the deepest, most extreme shadows of dark matter, dark energy, and black holes. And I want you to take away this one thought. The fact that we only understand 5% of our universe isn't a failure of science. It is an incredible, beautiful invitation. Human curiosity has always been the ultimate engine of discovery.
It really is. Every single time we peer deeper into the cosmos, or build a better sensor, or write a new equation, we find more magnificent mysteries waiting for us. So, the final provocative question we want to leave you with today is this. Will our relentless human curiosity eventually illuminate this haunting darkness? Or are there fundamental limits to our understanding that we can never, ever cross? Thank you so much for exploring the great unknown with us in this explainer. Keep looking up, stay curious, and keep questioning everything.